My voice is audible to you?
Yes, sir.
Okay, right. I'm continuing. Now I'm going to start the. Actually, this link is provided for the paper 8. Instead of our sir is somewhat busy, we are rearranging the sessions. Due to that reason, I'm going to start the paper 5. In that paper 5, the block 3, that is organic photochemistry. The title is Organic Photochemistry. Is my screen is visible to you all? Are you following my screen?
Yes, sir.
Yes.
Okay, right. Like I need some your responses whenever I am asking. Otherwise, I can't move. Right. Then in this we have 5 units. The unit 1, unit 11 actually in the book. Unit 11 is the electronic transitions. Electronic transitions. And the second one is, that is unit 12, photochemical reactions of carbonyl compounds and their derivatives. Photochemistry of carbonyl compounds and their derivatives. Okay. Unit 13 is photochemistry of some olefins. Photochemistry of olefins. Next to unit 14, the fourth one. Photochemistry of aromatic compounds and their isomers and are substituted aromatic. Photochemistry of aromatic compounds. Last unit, that is the 5th unit, that is 15th unit. Photochemistry of some nitrogen compounds and oxygen compounds. That is photochemistry of peroxides, nitrates, hypohalites, azo compounds or azo compounds and diazo compounds. Okay, these are the 5 lessons are included in this block. Now we are going to start the first unit, that is the 11th unit. Its title is Electronic Transitions. This is the unit 1, Electronic Transition. Now, before going to the topic, I would just like asking you to, what is transition? What is transition? What is transition?
Electron is excited to ground state to excited state.
I am asking you to, what is transition? With general word meaning, I am asking transition. Transition means frequent changing.
Means transfer.
Yes, frequent changing. Okay. Here also, electrons, we know that every element or every molecule containing elements or atoms are having the electrons. Those electrons are getting excited whenever they are observing the energy or the change in the energy of their states. It responsible for the electrons will be undergoing the change in their energies due to the transition. That is called electron transitions, electronic transitions. Now, we see that we have three kinds of electrons. Actually, all the organic compounds are most of them. Most of the organic compounds are covalent in nature, right? Covalent in nature. Therefore, generally we see in the organic chemistry what kind of bonds? Sigma bond and phi bond. These are the two kinds of bonds we are generally seen. Therefore, the electrons which are involved in the sigma bond are sigma electrons. Whatever the bonded electrons in the pi bond is called pi electrons. We call it as. Just a minute. Okay. Now, other than these pi electrons and sigma electrons, we have frequently seen that a pair of electrons on the atoms in the molecule. Suppose if you consider the oxygen, there is a having, it is a two pair of electrons in most of the cases if it is with the divalent. Okay. Whenever we see in the sulfur, it is having lone pairs. And if you observe in the ammonia or other nitrogen compounds, it is having the lone pairs. Okay, these pair of electrons are called lone pair of electrons. These are also indicated with the N bonded or non-bonded electrons, N electrons. Okay, these three electrons are the generally seen in the organic molecules. These are the three kinds of electrons are generally seen in the organic molecules. Therefore, these electrons, whenever we are subjecting to the heat or that is thermal conditions or photochemical conditions or any other conditions, that means we are providing energy. These electrons are gets excited from their ground level to next energy level. This is called electronic transitions. Now, these three kinds of electrons are undergoing the following electronic transit. Suppose the first you come into the sigma electron, suppose two electrons are there, or if we believe one electron is there in the bond. Therefore, it gets excited whenever we are providing energies in the form of thermal or photochemical. Now, this electron or any one of electron gets excited. Now this level is called sigma star. Sigma star. Now the between level is called non-bonding energy level. Non-bonding energy level. This is the bonding molecular orbital energy level. This is the anti-bonding molecular orbital energy. Now after gets excitation, whatever it leads to the formation of first excited state of sigma electron. That is sigma electron is excited from first excited state to ground state to first excited state. Right. This is the ground state. This is the first excited state. Okay. Similarly, n electrons or 5 electrons. If you take the 5 electrons, this kind of electron transition generally seen in saturated bonds containing compounds. Saturated bonds containing compounds such as alkanes, cycloalkanes. In these cases, we are generally seeing this kind of transition. Sigma to sigma star electron transitions. Now, when you coming to the pi electron transition, okay, this is the non-bonding energy level. Non-bonding energy level. Now the pi orbital, which is containing 2 electrons, these are called pi electrons. These pi electrons on providing of light energy or thermal energy, this will be gets excited to the next energy level. This is the first excited state level, is the pi star. Now after excitation, it leads to the formation of first excited state. It is having 1 electron, and pi star, that is the first excited state level, is having 1 electron. Right. This is the ground state. This is the excited state. Right. Now, this transition, in the first case, in this case, we call it as sigma to sigma star electron transition. Now, this is called pi to pi electron transition. Pi to pi electron transition. Now, where we seen these kind of electron transitions, where the unsaturated bonds containing compounds. Unsaturated bonds containing compounds. Okay, my screen is visible to you all. Is it to my sliding? My pen movement is observed or not?
Yes, sir. Yes, sir. Yes.
Now, unsaturated compounds containing compounds. What are the unsaturated bonds containing compounds? Olefins, alkenes, alkynes, and aromatic compounds, and dienes. dienes. These are all involving this kind of electronic transition. These are very important. Please remember where I am giving the examples. Those things we are discussing in future, right? Next. Right. Next one, N bond. Generally, we have this is the 5 and 5-star electronic transition states, and there is a non-bonding energy level. Non-bonding energy level. In this non-bonding energy level, there is a pair of electrons. Suppose what kind of molecules it is, this kind of electron transition. Suppose these transitions are shown by the compounds with lone pair of electrons. Lone pair of electrons. What kind of compounds that are? Suppose you take carbonyl compounds. Carbonyl compounds. Generally seen this kind of transitions in carbonyl compounds. What's happening? If you see the compounds which are having the oxo group, this is called oxo group. C double bond O. This is the C double bond O oxo group. This oxo group is having a sigma bond, pi bond, and this lone pair of electrons. Oxygen is having lone pair of. In such case, these pair of electrons first undergoing the electron transition, because these are the loosely held electrons easily polarized by the energy. Therefore, they get easily excited. Now, if you see the energy gap also, when you compare the 5 and 5-star energy levels, the gap between the 5-star, 5 is more, but the gap between the N and 5-star is less. Due to that reason, whenever we are providing the energy, the less energy, even though we are providing the less energy, the energy is sufficient to get excite the N electron to 5-star. Now it leads to the formation of the electron transition of N to 5-star state. There is no disturbance in the 5 molecular orbital, but the disturbance in the electron which is excited from N to 5-star. Now this kind of transition is called N to 5-star transition. N to 5-star electron transition. N to 5-star electron transition. Okay. Generally, we seen this kind, but whenever we are going to discussing the electron transitions theoretically, suppose if a molecule is having the sigma bond electrons, right? 5 bond electrons. This is a sigma, and its anti-bonding orbital is sigma star, and 5, its anti-bonding energy level is 5-star. And this is, suppose if we treat it is a non-bonding energy level, it is also having non-bonded electrons. That means it is having a pair of sigma electrons, a pair of pi electrons, a pair of n electrons. Now, it has the possibility to undergo the electronic transitions. I will show here how many possibilities are there theoretically. Right. Now, sigma to sigma star. This is the one electron transition. That means the electron is excited from sigma to sigma star, from to here. Now, this is one. You give the rank 1. Right. The second one is sigma to 5-star. Sigma to 5-star. These are all the theoretical possibilities I am explaining. Sigma to 5-star. Then the third one, 5 to sigma star. And fourth one, 5 to 5-star. Fifth one is N to sigma star. And sixth one is N to 5-star. These 6 kinds of electron transitions are possible. 6 kinds of electron transitions are possible. When we coming to the first one, if you see here, the energy gap between the sigma and sigma star is very large. The gap between the sigma and sigma star is very large. When you coming to, this is the energy gap. Okay. The length of arrow itself indicates the gap between the sigma and sigma star. Right. Now, this is the high energy electron transition. High energy electron transition. Right. Energetically, it is forbidden. It will not happen because that much of energy we cannot provide. But that is the first, or it is difficult to provide that energy. That is first thing. And second thing, even though it is symmetrically possible, most of the organic compounds will not undergo any sigma star electron transitions. Electron transition. Very rarely or very little number of compounds are undergoing sigma star electron transition, because this is symmetrically allowed, energetically forbidden. Please remember that word. Symmetrically allowed, or energetically forbidden. Energetically forbidden. Right. Symmetrically, sometimes we mention as geometrically. Geometrically allowed. Because sigma and sigma star both are in the same plane. Whenever we are discussing about the symmetry, it is a different topic. Symmetry of the orbitals, sigma and phi star, sigma star, n electron, n orbitals. Symmetry is the separate discussion. Okay. Now, here, sigma to phi star. This is also somewhat higher energy, but in the rank 2, the energy gap is so high. Right? This is the energy gap. This is suppose E1. This is the energy gap is E2. That is, E1 is greater than E2. Somewhat it is less energy when compared to the sigma to sigma star, but even though it is the higher energy, it is not possible energetically. Therefore, this is also higher energy electron transition. Higher energy electron transition. When we coming to and energetically forbidden, that is the one thing, because higher energy. The second thing is these two are having different symmetries. Different symmetry. What is the symmetry? Generally, orbital symmetry is expressed in the form, in the name of, in the terminology Z-rayed and unz-rayed. The Z-rayed is having the same shape. Z-rayed likes the G-rayed, unz-rayed likes the unz-rayed. Okay. Therefore, the electron transition is also involving Z-rayed to Z-rayed, unz-rayed to G-rayed, unz-rayed to unz-rayed. Okay. Whenever the electron transition is undergoing G-rayed to unz-rayed, is geometrically and symmetrically both ways it is forbidden. Okay. Sometimes, if it is the less energy, sometimes it is the less energy, and Z-rayed to unz-rayed is allowed. Symmetrically forbidden, but it is happening because of the energy availability. It requires a little energy. Therefore, whenever we are providing a little energy, they undergoing this spatial arrangement. They arrange it to spatial suitable spatial arrangement. They can undergoing the electron transition. Okay. Now here also phi to sigma star. Now when you look into here, phi to sigma star. This is also almost equal to the second one. This is also higher energy electron transition. Therefore, when we compare to the both 2 and 3, more or less same energy. This is when you come into it is labeled as E3, more or less approximately equal energy. Right? Then this is also forbidden. This is also forbidden. This is also forbidden. Right? Energetically forbidden, but symmetrically allowed it is. This one is the energetically forbidden and symmetrically forbidden. This one is also energetically forbidden and symmetrically forbidden. Now coming to the phi to phi star. Now look at here. The energy gap phi to phi star, when we compare to the remaining 3, it is the less energy. This is E4, right? Therefore, it is E3 is greater than E4. E3 is greater than E4. Therefore, it is the energetically lower energy transition. The first thing. The second thing is symmetrically is also allowed. 0 to 0 transition and energetically allowed. Both ways it is allowed. Therefore, in the olefins and sometimes carbonyl compounds, the 5 to 5 star electron transitions is more likely happen. This is the highly allowed electron transition. Next, N2 sigma star, when we coming to the N2 5 star, N2 sigma star, this is the almost it is the energy having the E4 that is equal to the E5 also, but somewhat lesser energy, but symmetrically forbidden. Symmetrically forbidden. Due to that reason, it is not allowed. Not allowed transition. Next, last one. N2 5 star. When you're coming to this here. N2 5 star. Look at here in comparing all the arrows, this length the length of this arrow is very little. But physically of watching this arrow length, the energy is also same. E5, sorry, E6. E6. Okay. E6 is somewhat, E4 is greater than E5, and E5 is greater than E6. This is the energy order of the transitions. Energy order of the transitions. And here, actually, this is the zeroed symmetry. It is unzeroed symmetry. Both are having the different symmetries. However, the energy is allowed. Simply we provide the little energy that get excited to the pi star. The n electron gets excited to pi star. Therefore, energetically it is allowed, but symmetrically forbidden. Symmetrically forbidden. Right. Now, we can see the more likely, yeah, Mr. Jayalakshmi, sorry, Jayalakshmi is raised the hand. Is there any doubt? Jayalakshmi, you are raising the hand. Is there any doubt? Okay. You can ask any doubt. Don't feel shy. Okay. If you have any doubt regarding the subject, you can ask me. I will clarify during the class. Don't worry about that. Okay. No one is questioning you why you are asking question, why you are. Okay. No one is asking like that. You can ask the question and clarify that. Right. Now the allowed transitions are actually energetically forbidden, but 5 to 5 star, sigma to sigma star is allowed, symmetrically allowed. Symmetrically allowed, but very rarely seen this, very rare electron transition. Very rare electron transition. When we're coming to the 5 to 5 star, symmetrically and energetically, both ways it is allowed. Symmetrically and energetically, both ways it is allowed. N to 5 star, it is symmetrically forbidden. Symmetrically forbidden. But energy is allowed to are energetically allowed. Therefore, we can see these three kinds of electron transitions in the inorganic molecules. Now, when you comparing the energies, N2 5 star is the lower energy, and the 5 to 5 star, and then the sigma star. right? These things you need to remember, right? Now, after we are understanding these transitions, you need to understand this, the minimum energy requirement for each transition. Suppose in the case, in the sigma star transitions, here we are providing the energy in the form of thermal or heat. Suppose we are providing the light energy, it requires only 154 nanometers of light energy. The frequency of light is 154 nanometers, right? Next, when you come into the 5 star, the frequency, lower frequency, the higher energy, higher frequency, lower energy, right? When you come into the 5 star, it is approximately 180 nanometers. It requires 180 nanometers. Then in the 5 star transitions, it requires almost approximately 270 nanometers of the light. Wavelength of the light is higher the wavelength, lower energy. Lower the wavelength, higher energy. That is inversely proportional. Wavelength is inversely proportional to energy. Okay. After understanding these things, you need to understand the detail in the detailed way about the orbitals in the carbonyl compounds. Because in the carbonyl compounds, we generally seen two kinds of electron transitions. Not the sigma star, except sigma star. We can see these transitions. What are the n to 5 star transitions and 5 to 5 star transitions? Now, first coming to the structural representation of carbonyl group. This is a carbonyl group. In this, the carbon is sp2 hybridization, and this carbon is sp hybridized. Oxygen is the sp hybridized. Now, when we coming to the orbital structure of the carbon, according to the hybridization, it is having sp2 hybridization. That means total 3 sp2 hybrid orbitals and 1 unhybridized orbital. Right? How these 3 sp2 hybrid orbitals are arranged? These 3 sp2 hybrid orbitals are arranged in the single one plane. That means all these 3 hybrid orbitals are sp2, sp2, sp2 of the carbon. Right? These are arranged in the single plane. Suppose a 2-dimensional paper, you take it. If you place this object on the plane, these three orbitals are present in the same plane. That is called collinear or coplanar. Right? Okay. Next, it is having the unhybridized p orbital. That unhybridized p orbital is perpendicular to the plane which these 3 orbitals are present. That means which is perpendicular like this. These 3 orbitals are existing on the same plane like this. Now, this is the unhybridized p orbital. This is the orbital structure of carbon in the carbonyl carbon. Yes, someone is asking. Yeah, Saidulu, tell me.
Sir, oxygen also sp2 hybridization, sir.
No,
sp ra, sir.
no. In the ground state, it shows sp. In the ground state, it shows sp. Right. Okay. Just
Okay,
a
sir.
minute. I will check it out. Okay. Okay, right. Only SPL. That is having, it shows the SPR. Okay. Now, how it is SP, I will show you. This is the oxygen. Now, it is having 2 sp orbitals. 2 sp orbitals. One is the 2 are the unhybridized p orbitals. Right. The two sp orbitals are like this. One of the sp orbital is like this. The other one is, it is interacting with the covalent bond of the sp2 and sp hybrid orbital of oxygen. This is the sigma bond. The sigma bond is established between these two. Okay, in the carbonyl compound, one is the sigma, one is the phi. The bond is, the sigma bond is this one. There is a bond between the sp2 hybrid orbital of carbon and sp hybrid orbital of carbon. Oxygen. Okay, the remaining p orbitals, which are perpendicular to these two sp orbitals and each other. Now, how it is? This is one p orbital, and other p orbital is perpendicular to the all the four. Look at it, how it is arranged. This is a straight line. These two are perpendicular, right? Now, other and another one is there. Look at here. Here, the three lines are perpendicular to each other. All the three lines are perpendicular. Similarly, these hybrid orbitals are also arranged like this, right? Now, how the pi bond is established? Now, the oxygen is having the two pair of electrons. One is the one lone pair and a second lone. One lone pair is present in sp2 hybrid orbital, sp hybrid orbital, and another lone pair is present in the sp orbital, just p orbital. Now, there is another pi bond is there. The pi bond is established between this unhybridated p orbital of carbon and unhybridated orbital of oxygen. This is the pi bond. This is the structural arrangement of carbonyl or oxo group. That thing is very, you need to remember, very important to understand the several reactions in the photochemistry. Okay, right. Now, these are the general excitations. These are the general excitations. Now, when a bonding molecular orbital is containing, suppose it may be a sigma bonding molecular orbital or a pi bonding molecular orbital, whatever it may be, it is a bonding molecular orbital. It is containing a pair of, suppose if it is a pair of electrons with the opposite spin. Remember that, opposite spin. Now, when you provide the energy, this is the non-bonding energy level. Non-bonding energy level. Now, whenever we are providing energy, the electron is excited from this bonding energy level to higher energy. Now, during this excitation, this electron may retain its spin. That means, after excitation, it is having the same spin which is having in the ground state, or it may be changed to opposite spin, or it is transformed to other spin, right? That means the electron may be excited in the two ways. The first way, suppose it is changed its spin, inverted its spin, that is called inversion of spin. One of the electron is there, it is having this spin. It is a retention of spin. This is called inversion of spin. Okay, this is called retention. This is inversion. Right. Inversion spin and retention. What's happening in the inversion and retention? You just simply understand that. When it is retained its spin, therefore, there is no change in its state. Even though it is in the first excited state, its energy state is expressed in two ways. With respect to the spin value by using the that is called multiplicity. By calculating the multiplicity with using the formula 2s mod plus 1. By using this formula, we can calculate the spin. Or sometimes, that is this value j is equal to coupling constant, j is equal, or multiplicity j is equal to 2s into 2s plus 1, where s is equal to spin of electron. The spin of electron is minus of or plus of. Suppose in this case, this electron is having the plus of. This electron is having the minus of. The total spin, the sum. C S is equal to sum of the spin of electron. Sum of the spin value for this particular electronic configuration plus of minus of. Then what is that? Both will be cancelled. Spin is 0. Now J is equal to 2 plus 2 into 0 plus 1. Then what is the value? 1. Therefore, that is multiplicity is 1. Multiplicity equal to 1 for this particular arrangement of electronic configuration. Now coming to here, this is the plus of, excuse me, plus of. This is also plus of. Now what is the sum of spin?
1.
Yes, plus into plus of equal to 1. Now J is equal to 2s plus 1. And we apply the mod. Okay. Why we are going to apply mod, I will tell you later. Okay. 2 into 1 plus 1. The J value is equal to 3. This is called triplet state. However, it is the excited state, the triplet excited state. Triplet excited state. These two are the excited states. After electron excited to first excitation state, these two are the first excited states. Again, this first excited state or upper excited state or upper excited state, all maybe exist in the two forms. One is the singlet excited state and another one is the triplet excited state. Got my point? Are you following? Okay. Now, I will go to the next topic. Okay. I think it is up to this you are clear. Do you have any doubts? Do you have any doubts?
No, sir.
Okay, thank you. Okay, just give me 2 minutes. I will come back to you. Just to give 2 to 5 minutes. Okay, stay in line, please. I just have
Okay, sir.
some conversation with. Okay.
Okay. Okay.
Right. Sorry friends, కొంచెం late అయింది. Okay, right. Now this is about the transitions. When you comparing the energies, that means what energies we have the singlet energy, that is singlet excited state and triplet excited state. Whenever we are comparing these energy states, excited state energies, sometimes triplet state is having the higher energy, sometimes singlet state is having the higher energy. Okay, how it is possible? Suppose if we consider this is the energy profile diagram of 5 to 5 star electron transition. This is the non-bonding energy level. This is the 5 orbital bonding molecular orbital, and this is the 5 star orbital, right? Now it is also having non-bonded electrons, right? Now in the 5 electrons present in the 5 BMO bonding molecular orbitals, that is 5 star anti-bonding molecular orbitals, and N non-bonding molecular orbital. Non-bonding molecular orbitals. N means non-bonding molecular orbital. It is also having 2 electrons. Both are having 2 electrons. Whenever we are providing the energy, it is the lower energy frequency of light. That means we are providing 270 nanometers light irradiation. That is undergoing N to 5 star transition. At that particular lower energy, it is only undergoing N to 5 star transition. Now it leads to use the 2 kinds of excited states as we are discussed earlier. This is the non-bonding energy level, non-bonding orbital, 5 star orbital, 5 orbital, N orbital, and 5 star orbital. Now, at that lower energy state, the electron is excited from this N non-bonded level to this 5 star energy level. Therefore, during the excitation, it is retained the spin, or it may be undergoing the inversion spin. It may undergoing the inversion of spin. 5 molecular orbital, N molecular orbital, 5 star molecular orbital. After excitation, here the spin may be inverted, inversion spin. Now these are called, this is the singlet excited state, this is the triplet excited state. Simply we call it as triplet excited state. Now simply I am labeling it as 1 means singlet, N2 5 star transition. We can also call simply for this particular kind of transitions, this one is S1 state, S1 singlet state, S1 singlet state. Then what is the S2 state? I will explain that. What is the S2 state? Okay, this is the S1 state. Now when you come into this one, here the electron undergoing the spin inversion. Now this transition is 3 N2 5 star. 3 means triplet state. The multiplicity is 3, triplet state. Or it can also indicate with the T1 state. This is also indicated with the T1 state. Now, you see that the energy, generally, this is the allowed transition. This is the allowed one, because whenever the electron is undergoing the electron transition, the spin inversion is prohibited. Spin inversion is not preferably takes place. That is the reason whenever the transition is involving spin inversion or changing its spin, that is forbidden transition. Therefore, this transition is forbidden. Right? Generally, sometimes we can see indicated the crossing that line arrow. Right? Now, when we comparing the energies, the energy of, that is the energy which is required for the transition is, it was singlet is more is greater than energy of 3 into 5 star. Why it is having the higher energy, why it is having lesser energy, I will give you the clarity in the next session, next topic. Okay. Okay, this is the transitions N to 5 star, which is involving to produce the singlet and triplet excited states. Okay. Next. Someone is captive. Yes. Right. Next, coming to this for the same molecule, same carbonyl compound, you take it. Same carbonyl compound, you can take it. The electron transition for that particular molecule. That means if you believe that that is having n electrons, n non-bonded electrons, and it is also having 5 electrons. Therefore, this must be a carbonyl compound. It must be a carbonyl compound. Whenever it is irradiated with the higher energy frequency radiation or lower wavelength, 185 nanometer light, we are irradiating it. It is undergoing at the particular energy frequency, light energy, that is undergoing 5 to 5 star transition, not the N to 5 star. N to 5 star will be forbidden because the energy is permitted to excitation of 5 to 5 star, not the N to 5 star. Even though it is having lower energy, that energy is crossed, you are providing much energy. Therefore, N to 5 star is forbidden, then 5 to 5 star is takes place. This is the 5 star energy level. Therefore, the electron is excited from this ground state to excited state. Electron is excited to from ground state to excited state. Now here also we can get the two energy excited state, two kinds of excited state, which is one of them which is involving the retention of configuration. One of them is involving the retention of configuration. Now it is with the I'm changing. Okay, right. This is the retention of configuration, retention of the spin of the electron. Next, the second one, right? It is undergoing the inversion spin like that. Right. This is the singlet excited state. Singlet excited state. It is the triplet excited state. Triplet excited state. Now, how will you represent it? It is once the one represents the singlet, 5 to 5 star excited state. This is also called S2 state. Previously, that's why I told you previously. I will tell you what is S2. This is the S2. S1 is this one. S2 is the N to 5 star electron transition. S1 is S2 is the 5 to 5 star transition. That S1 is N to 5 star transition. N to 5 star transition. And S2 is the 5 to 5 star transition. Carefully remember that. Okay. Now we will represent like this state. And you come to the triplet state. It is the a 3 superscript 5 to 5 star, or it is represented with the T2 state. Previously, that what is the T1 state? T1 state is the just a minute. This one singlet and this one is also singlet. We need to always represent whether it is a singlet or triplet. The T1 is the triplet state of N2 5 star, and T2 state is the triplet state of 5 to 5 star state. Okay, this is about the general excited states and general electronic excitations. Now, these excitations will give the several kinds of decaying process, because once the electron is excited from ground level to higher energy level, they are undergoing the decay. For example, if we are heating a object, after heating some, we are switch off the heat source. Then what's happening? It came back to room temperature. That is called decay. Simply, that is called decay. Similarly, electrons are undergoing the excitation whenever we are providing the energy. After take off that energy, they slowly come back to ground level. That is called decay. Now, during this decaying, that leads to produce several energy levels than the excited state, lower energy levels than the excited state. That will be explained by the Jablonski diagram. In the next session, we will discuss about the Jablonski diagram. Why? Because I am stopping here is, once we start the Jablonski diagram discussion, it takes at least 25 minutes. On a specific topic, it requires 25 minutes. That is the reason I'm stopping the topic now today. And in the tomorrow session, we'll continue with the Jablonski diagram. Okay. Once the Jablonski diagram completed, we'll move to the second unit. Okay. Now I'm stopping now. Okay. Do you have any doubt? I will give you 5 minutes. You can ask me. I will clarify. Yes. Is there any doubts? Please.
No, sir. No, sir.
No doubt.
No. Is there any Vizag, Tirupati, Warangal people joined? Okay. 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 Thank you.
Thank you, sir. Thank you.
Thank you.
Thank you, sir.